All right. So to begin this presentation, I'm going to give an outline of what we're going to talk about. I'm first going to give some background on, so this is kind of an interdisciplinary thesis I've done because alternative stable states and the Lee effect are two concepts from ecology that I will be discussing. And then we'll be talking about some background in epidemiological modeling. And then it's going to get onto the part where we're at the thesis body. I'm going to give the formulation of the SIR model that this thesis is about and the way that we sort of generalize it in this thesis. And then I'm going to prove some nice things about this model, prove the existence and uniqueness of solutions for certain initial conditions. I will give a formula for all the equilibrium solutions. And then I will show that these equilibrium solutions are stable or under what conditions they are stable. And then I will formulate the stochastic model and then give some numerical examples in the end. All right. So in ecology, alternative stable states refers to the occurrence of multiple stable states of an ecosystem. So the idea is that we could have an ecosystem dependent on a bunch of parameters. And then for the same set of values for these parameters, it might be in one state or another. So like temperature, latitude, and stuff like that. All that might be the same, but this same place could be a tundra, or it could be like some kind of a forested woodland. And the idea is that systems may transition between these states due to a change in parameters or due to some perturbation of variables. And I took this from the Beisner paper I sort of cited. I like to think about the parameters as kind of the like environmental conditions. And kind of a good visual is like a ball rolling from one state to another, where it's kind of stable when it's inside this bowl. So if we temporarily shift the parameters in such a way, it might cause it to be attracted to another stable state, and then it will go towards there. Or if we start in one stable state and we're temporarily pushed up, we might get to some point where we're instead attracted to this other stable state. So we can kind of model catastrophic ecosystem shifts where you might not be able to go back. I believe that's called hysteresis. But the applicability may currently be a bit limited. Okay, now we're going to talk about the Lee effect and what I was able to figure out from it. So the most general definition I've heard is that the Lee effect is a positive relationship between components of individual fitness and the population or population density. And in practice, this is exhibited as a positive correlation between population growth and population density whenever we're at low densities in particular. So just like making a comment here, these components of individual fitness, it's not necessarily always going to lead to a positive relationship between the reproduction rate and the population density. As a matter of fact, there's like a specific curve for the Lee effect that we see because this trait of individual fitness might actually relate to the death rate of the species that we're looking at. So as we increase population density, the death rate actually increases. So we actually have some kind of negative correlation between the rate of change and the population density. And this could be caused due to some breakdown in social interactions due to failure to locate mates, disruption in cooperative behavior at low population, and increase in vigilance efforts. So the Lee effect is commonly modeled with this following differential equation up here, where D is kind of like our death rate is greater than 0, or it's just some kind of a sort of scaling constant. And then K2 is greater than K1. And so I drew the graph right here. This is for the case whenever we set K to be 10 and K1 to be 3. Pardon me. Okay. So the idea is that if we start at some value for n, so n is going to be our total population. Let's say we start at n is equal to 8. Then dn over dt, which is the rate of change of n, is going to be positive. So it's going to increase until it hits 0. So dn over dt is 0. It's going to stay there. We call wherever it goes through the 0 axis here, whenever dn over dt is 0, we call that a stable, or sorry, we just call it an equilibrium. And so as we see, whenever we also get higher than 10, dn over dt is going to be negative, so we go down to 10. And that's actually how we define our stable equilibrium, or equilibria, is that whenever you start sufficiently close to the equilibrium, you're going to be attracted to the equilibrium as time increases. So we actually have another stable equilibrium also, because if we start to the left of n is equal to 3, it's going to be negative, so it's going to kind of decrease until you reach 0, and then it's going to be stable there. So that's kind of like our, this is kind of our case for a population collapse right there. So you can kind of see how this might model breakdowns in population once the population gets below a certain point, although it may be stable at a certain point as well. And it's also worth noting that if you're exactly at this equilibrium right here, you're also not going to move, but this is an unstable equilibrium, because if we start a little bit away from it, you're going to move away from the equilibrium. So now I'm going to talk about some background in epidemiological modeling. The study of disease occurrence is epidemiology. And while there's a lot of mechanisms for disease transfer, we are interested in person-to-person transfer. It is normally difficult to comprehend the dynamics of transmission across a whole population, but we can use knowledge of individual transmissions. So transmissions from one individual to whoever they infect, to better predict the behavior through a mathematical model. And so epidemiology benefits from mathematical models because it's not a field where we can really get experimental data from in an ethical manner. Hypothetically, we're not going to be infecting populations to get data from it. And also data may be unreliable due to undercounting of infections and such. And these models allow us to make prescriptions to limit disease. That's actually what we do in the paper that we're trying to get published. Yeah, we do it with experiments. I mean, PETA would say it's. Yeah. All right.
Oh, no.
You say it's a hypothetical.
And
if you say no or yes, it is, or no, it's not, then I have other questions.
I'd like to think it's a bit like. I mean, we could definitely get data from that, actually. Yeah. All right. So we're going to talk about some previous work on epidemiological models, just give some background of papers that have been written. Kang and Chavez in 2012 provided a disease model with the Ali effect and dispersion. There's going to be a pattern with each of these. Friedman and Yukabu in 2012 obtained conditions that guarantee post-population persistence or extinction, also using the Ali effect. And then our own professor, Ikane Yaques, they studied a seasonal SAR model, meta-population model with an Ali effect to investigate the sylvatic plague within prairie dog colonies. And each of these have used this equation of the Ali effect that I talked about earlier in order to simulate those stable states. And we will see that this kind of gives us an immutable, potentially unrealistic curve to real data about some of the demographic characteristics of the model, such as the per capita birth rate and per capita crowding difference. All right. So now we're going to go into the background of the SIR model. It is a common form of epidemiological modeling, and it classifies individuals according to their status, whether or not they are susceptible to infection, we call that the S compartment. Whether or not they are infected, we call that the I compartment. And whether or not they are removed or immune or isolated, we call that the R compartment. Sometimes R also includes individuals who have died, but in our case, it will not here. And basically, each of these individuals are represented by time-dependent variables. So S, I, and R are all dependent on time. And we can make a differential equation model from this. It will be a system of differential equations where we define ds over dt, di over dt, and dr over dt. And we're going to build up this model by making some assumptions, which I will go into now. Our assumption is that newborns are susceptible to the infection at birth, with the per capita birth rate being this function b of n, which is a continuously differentiable function of n, where it will be positive for whenever n is not negative. And then the per capita death rate is going to be a continuous monotone function of n, which may be higher for infected individuals. And we formulate it in such a way that we have a function d of n and a function di of n, and they're only going to differ by a constant. So d of n is going to be d plus some c of n, and then di of n is going to be this lowercase di plus c of n, where di is going to be greater than d, so di is going to be greater than d here. And we also require that c of n is going to be continuous and also Lipschitz continuous, which we will talk about what that means later, and it's going to be non-negative. So the larger the population, the greater the death rate, because this is a monotone function. And these two assumptions are kind of the really important ones right here, because this lets us pick out the sort of curves that we use for b of n and d of n, basically. Whenever we use the that sort of Lee effect equation I talked about earlier, it forces these to be very particular curves. But in this formulation, we can fit bn and dn to quantitative or qualitative data. All right, that's like the main point. So our third assumption is going to be that the per capita rate of transmission that susceptible individuals will become infected is beta times I. So that's the per capita rate. It's going to be dependent on how many infected individuals there are. This is for host-host transmission. And then the per capita rate of recovery is going to be a constant gamma. And then the proportion of recovered individuals that return to the susceptible class is some alpha in the closed intervals 0 to 1. So this is kind of a proportion of individuals who will recover and be susceptible again, which means the complement of that proportion, 1 minus alpha, that's going to be the people who will become immune to the disease. So they're going to go into the R compartment. If infectious individuals are infectious for life, then gamma is just going to be 0. And then the per capita rate at which susceptible individuals become vaccinated is going to be a constant V. And I drew up a compartmental diagram of the differential equation system that we get from those assumptions. We get that this was per capita, so it's going to be multiplied by n. That's the rate of births that we get. Then we have our respective rates of death. We have our vaccination rate, bringing individuals from being susceptible to removed. And then beta times I was the per capita rate that susceptible individuals become infected. So it's going to be multiplied by S in order to give us the rate that individuals become infected. And then these terms with the gamma are going to be our rates of recovery. So we have alpha many individuals, or a proportion of alpha many individuals go back to being susceptible, and a 1 minus alpha proportion of individuals go to being removed or immune. Okay. So the system of ordinary differential equations that satisfy these assumptions is given by this. This is just me writing out the compartmental diagram in our differential equation form. And we're going to let n be our total population, s plus I plus r. Because B and D, I'm writing out D in the form D plus Cn in this model. They both depend on the total population n. All right. And we note that this model contains as special cases the SI and SIS models. Basically, if we set gamma to be 0 and also the vaccination rate to be 0, then what happens is individuals become infected, just stay infected. So we only have a flow from S to I. If we increase gamma back up, but leave alpha to be 1, then it becomes an SIS model, which means it just goes from S to being infected and then back to being susceptible. Those are just two different, more simple models than the SIR model. Okay, now we're going to move on. We say that a model is biologically well-defined if our variables remain non-negative for all non-negative initial conditions. Because in our case, it's not going to make sense that we have a negative infected population, for example, or a negative susceptible population. Okay, so we're going to demonstrate the conditions for existence and uniqueness of the solution to this system of differential equations. So now we have to dive into some mathematical preliminaries of it. We're first going to define the norm. It is a function from a vector space to the real numbers that sort of gives us a magnitude from 0. And it satisfies these conditions, which all kind of make sense. Our measurements are all going to be greater than or equal to 0. And the measurement, the norm is going to be 0 if and only if we're measuring the 0 vector. All right. And then if we scale a vector by some amount c, then the norm, or like the measurement of it that we get, is it's going to be that amount scaled by the absolute value of c. And then our third condition there is the triangle inequality works here. All right. So these are the two norms that are going to be used in the existence and uniqueness proof. On the set of continuous bounded real valued functions, they form a vector space whenever we're on some interval u. So we define the sup norm as being the absolute value of the supremum over all x of the outputs we get from the function. So the least upper bound of all those values. And then if we're looking at Rn, and we're going to let x be a vector from it, then the L1 norm is going to be the absolute value, the sum of the absolute values of all of our components. I think this one's called the Manhattan norm. Taxi cab. Okay.
It's also called-
All right. I see.
Inside that
Oh, where?
soup of that, of that, of that.
Oh, it should be inside. Yes, that is correct. Yeah. I would like to make a correction. The absolute value should be inside the supremum there. That's something else. All right. The norm lets us define this following stronger notion of continuity on a vector valued function. It is called Lipschitz continuity. And a function f on vector space is called Lipschitz continuous if it satisfies what is called the Lipschitz condition, which is what we have right here. It means that there exists a lambda greater than 0 such that the difference between, or the norm of the difference of f of x minus f of y is less than or equal to lambda times the difference of x minus y for all x and y in our vector space. Lambda is called the Lipschitz constant, and it can be demonstrated that a function that has a bounded derivative on some interval is Lipschitz continuous on it. And it goes the other way in the case if the function is continuous or continuously differentiable. All right. So this following theorem is one of the most important ones in the thesis. It gives us a sufficient condition for the existence of a local unique solution to the standard initial value problem of our system. It's called the Picard-Lindelof theorem. So we're going to let D be in, we call it R cross Rn because this R is kind of going to be our time domain and this is going to be our space domain. We're letting D be an open rectangle that contains the point T naught X naught. This is our initial condition. And then we say, okay, if f from D to Rn, this is going to be our system. If it is a function that is continuous in T and then Lipschitz continuous in X, then there exists a neighborhood in T such that the initial value problem, which this is just saying that we set the rate of change of our X equal to this system. So this is our system of differential equations. The initial value problem has a unique solution X of T on that interval. All right. And we're going to pair this theorem with a theorem that sort of extends this, this local existence of a solution. This has the same setup as earlier. D is a subset of R cross Rn. And we're supposing that our system f from D to Rn is continuous. And then we say, if there exists a solution to the initial value problem, X of T on some interval, that's what Picard-Lindelof gives us. Then there's a continuation of X of T to a maximal interval of existence. And then we get to sort of specify what this maximal interval of existence is with this last part. If the interval from A to B is a maximal interval of existence for a solution X of T, then the pair T comma X of T should tend to the boundary of our domain as we go to one of the endpoints of our interval. And so the contrapositive of this last clause of the theorem is going to be useful in showing what our maximal interval of existence is. Because if you're going to the endpoint of your interval, say B, and you are not reaching the boundary of D, then it's not the maximal interval of existence. Right. So now we're going to go into the proof. The model given by equations 2 through 4, this is just the system of differential equations brought up earlier. We say it is biologically well-defined. We're going to show that. Then we have, if there exists n naught greater than 0 such that Bn minus Dn is less than 0 for all n greater than it, then the system is going to possess a unique global solution for each initial condition where all of the indices start out non-negative. All right. And so the sketch of the proof is that we're first going to show that it's biologically well-defined. The way that we do that is we're going to set S equal to 0 and then show that ds over dt is not negative. And then we do the same thing for I and for R. Basically, what that tells us is that if S, I, or R ever reach 0, then the rate of change is not going to be negative, so it's not going to decrease any further. And so what we get from that is that if we start out with a positive initial condition, it's never going to go negative after that. Now, just from doing some algebra with our system, our hypothesis, in particular this part, the Bn minus Dn less than 0, lets us conclude that if n is greater than n naught, then we get that dn over dt, the rate of change of n, is going to be negative, meaning that so there's this value of n naught somewhere where such that whenever we get higher than it, the rate of change is going to be negative. And because of that, and also combined with the fact that our system is biologically well-defined, it's going to imply that n of t is bounded. If you get up to a certain point and the rate of change is negative, then there's going to be some maximum value for n there. And it's bounded on t from 0 to infinity and thus has a supremum n star. All right. However, n of t does not necessarily have a maximum on 0 to infinity. So we're just going to let capital T be greater than 0. Then, due to the extreme value theorem, and because n of t is continuous, it has a maximum n tilde on 0 to t. And so because we also assume Bn, Dn, and Di of n are all continuous on that interval, by the extreme value theorem, they all also attain a maximum. And I'm going to write down their maximum by their sup norms because the supremum is going to be equal to the maximum in this case. Furthermore, because Bn is continuously differentiable, the derivative is going to be continuous on a closed interval. So also from the extreme value theorem, we get that it's bounded and it's thus Lipschitz continuous. And we're given that D and Di are Lipschitz continuous. So with that, we're basically able to, I don't show this part because it is a lot of math and a lot of writing. We're able to find a lambda using all of this where F is Lipschitz continuous on 0 to t. All right. So F is Lipschitz with respect to X on 0 to n. That should be 0 to t actually. And it is independent of t. So it's going to be continuous with respect to it, just vacuously. So by the Picard-Lindelof theorem, we have a unique local solution for each initial condition. F itself is continuous, so this local solution can be extended to a maximal interval of existence. We have that t comma x of t does not tend to the boundary of our domain as we go to capital T, as the norm of x of t, or well, the maximum value of it is going to be less than or equal to this n tilde, which is less than n star. So 0 to t is not the maximal interval of existence for any t, implying that it must extend all the way out to infinity using this sort of extension theorem of Picard-Lindelof that we brought up. So we have a unique global solution on 0 to infinity for each set of initial conditions, and that concludes our proof. So equilibrium solution occurs when, I wrote it down that way, but whenever ds over dt is equal to 0, di over dt is equal to 0, and dr over dt is equal to 0. This is just me writing it down as if we write SIR as x1, x2, x3. And it necessitates this condition right here, which is just the dynamics of dn over dt right there. We're going to let x sub e be our point at our equilibrium, and then n sub e is going to be our total population at our equilibrium. And then we get 3 equilibrium solutions at the end of it. We get a trivial equilibrium, we get a disease-free equilibrium, and we get an endemic equilibrium. And we have equations for all of them. Okay. If we get that I at our equilibrium is greater than 0, then it's going to necessitate this condition right here. And we're able to do a comparison of this. We use the next generation matrix method, which allows us to calculate the basic reproduction number of the system, which yields this. And what the basic reproduction number is for epidemiological models. It is the expected number of infections from one individual being infected. So the idea is that if R naught is greater than 1, the disease is going to spread and it should become endemic. If R naught is less than 1, it's going to start fading away. All right. And we can see that R naught being greater than 1 indeed corresponds to this condition that we have right here. All right. And something else that I'd like to note real quick right now is that, so DI and D, that's our sort of base death rate for infected individuals and not infected individuals. Whenever this is equal to each other, whenever DI is equal to D, then the whether or not our total population is at equilibrium depends only on N, so we're able to find the values directly from that. Otherwise, we have to solve the entire system and see when it is equal to 0. All right. So we found our equilibrium, and the idea is that R naught is going to tell us whenever our equilibrium are going to sort of be active or not. So whenever R naught is greater than 1, our disease should become endemic, which means only the trivial and endemic equilibrium are possible. Whenever R naught is less than 1, then we will be at the disease-free equilibrium, and the trivial equilibrium are going to be the only ones possible. And now we're going to show or demonstrate the stability of these equilibria. So to build background of that, we're going to consider the Jacobian. So the Jacobian of a vector value function is a matrix of all of its first order partial derivatives. And I like to remember that it's in such a way where each of the rows form a gradient of each component. So that's what I have right there. It's the definition of the Jacobian. And pardon me, the eigenvalues of the Jacobian are important in demonstrating the stability of our equilibrium solutions. So we're going to talk about eigenvalues a little bit. An eigenvalue of a matrix A is any value lambda, which could be a complex number as well, that satisfies for some vector in our space. If you multiply it by A, it's just going to get scaled by that constant. So AV is equal to lambda V for some V in our vector space. And so an important thing for our matrices is the characteristic polynomial. The characteristic polynomial of A is the polynomial P of lambda given by, you take the determinant of A minus lambda times the identity matrix. And the roots of the characteristic polynomial allow us to compute the eigenvalues of our matrix, as lambda naught in C is going to be an eigenvalue of our matrix if and only if it is a root of the characteristic polynomial. All right. And so this following theorem is going to let us use this to demonstrate the stability of a given equilibrium solution. We're going to let our system of differential equations be as we've stated earlier, but this time we're just going to say that we're given that it's independent of T. And we have an equilibrium point X sub E. we're going to let the Jacobian of f with respect to x evaluated at our equilibrium be j of xe. And the idea is that if all of the eigenvalues of this Jacobian at our equilibrium have negative real part, then the equilibrium is locally asymptotically stable. And there's a more specific definition of what that means there, but the important part is that that implies local stability, which means there's some region around it where if you're close enough to it, you're going to start going towards it as time goes on. Otherwise, we get that our equilibrium is unstable. So the idea is that we find the eigenvalues of the Jacobian through finding its characteristic polynomials and then calculating it. And then we demonstrate the real parts are negative to show an equilibrium is stable. That's kind of the sketch of how most of our proofs are going to go on now. Okay, so we're going to let K of NE be written as I have right there. Kind of looks gross because it's from chain rule and everything. And then this is what I have the Jacobian written out as. It is a very long matrix, and we actually I split it up into two different ones to make it be written easier. This equals sign should not be here actually. Okay. So that's what we get for the Jacobian. Now we're going to suppose that our system satisfies our assumptions, and we have this: if B at 0 minus D at 0 is less than 0, and if the basic reproduction number R naught is less than 1, and if B prime of NE minus C prime of NE is less than 0, then we get that the pair of the trivial and the disease-free equilibria are locally stable. All right. Now we're going to go through the proof of that, sort of using that sketch that I gave earlier. So this condition, B at 0 minus D at 0 being less than 0, is used to show that the trivial equilibrium is locally stable. So the Jacobian, whenever we are at 0, has these as our eigenvalues. And because di at 0 and d at 0 are both positive, and gamma and v are both positive, and we're all taking just negatives of these, those are obviously going to be negative. In lambda 3, from our hypothesis, remember, we are assuming that this is negative. So that's going to be negative. So all of the eigenvalues at 0 are negative, meaning that 0, our trivial equilibrium, is going to be a locally stable equilibrium. Similarly, we solve for the eigenvalues of our Jacobian at our disease-free equilibrium, where I is 0 in this case, because we're at the disease-free one. And it has these as our eigenvalues. And we have shown that lambda 1 and lambda 2 are indeed negative. We show this in the work of my thesis. And from our hypothesis, because this is just B prime of NE minus C prime of NE multiplied by NE, which is positive, we get that that is also negative. So this disease-free equilibrium is also stable. So now we're going to try to show the conditions for the stability of the endemic equilibrium. And we're not actually going to be able to get direct conditions for it, but we get that basically we're going to get it for the case that whenever di is equal to d, we're able to show it, but that there's some neighborhood of di above d where the endemic equilibrium will be stable. Okay. So we define this matrix J naught, and the idea is that this one is only going to differ from our Jacobian by a little bit, and this one's going to have easier eigenvalues to solve for. So we're going to show this lemma where if I sub e is greater than 0, so we're basically saying that we're at our endemic equilibrium, and B prime of NE minus C prime of NE is less than 0, then we have that all of the eigenvalues of J naught have a negative real part. And so like I said earlier, what we notice is that if di is equal to d, basically di of NE is equal to d of NE if and only if these are equal to each other. This is just going to become 0, so this entire term drops out, and then J naught is equal to our Jacobian. But if di is greater than d, then we need to do a bit more work for that. Okay, so the sketch of the proof is that we solve for the eigenvalues of J naught, and what we get for this eigenvalue, we already know that one's negative. That was the same one we did in our previous proof. We know it's negative from our hypothesis. what we get for our other eigenvalues is we get this sort of confusing looking expression, but it comes from the quadratic formula, which might make it look a bit more familiar. And we have expressions for A and B. Their particular expression doesn't matter too much to us, but all that matters with them is that they are positive. A and B are both positive. So then we split this into cases. Pardon me. If a squared minus 4b is less than or equal to 0, then our square root of a squared minus 4b is going to be imaginary. So then the only real part of lambda 1 and lambda 2 is going to be this 1/2 minus a, which is negative. So they're both going to have negative real parts. Now, if a squared minus 4b is greater than 0, then it's going to be obvious that lambda 2 is less than 0. But because a and b are greater than 0, I actually wrote this in the reverse way. It should be, that is right. A squared minus 4b is less than a squared because we're just taking away from this. So lambda 1 is going to actually equal, because a squared minus 4b is less than a squared, we can replace that in this square root to get that lambda 1 is less than 1/2 negative a plus a squared. That's just minus a plus a, so that's going to turn into 0. So lambda 1 is less than 0. So all of the eigenvalues have negative real part, and our proof is done. Remember, we're just proving that J naught, all the eigenvalues of it have a negative real part. Now, this following theorem is useful in comparing the eigenvalues of two matrices because it lets us compare the characteristic polynomials of them. So we're going to let P be a polynomial of degree n, and we're going to let x naught be one of the roots of the polynomial. So this is like somewhere on the complex plane with multiplicity mu, and then d is going to be the distance of that root to one of the other roots of P. Basically, we're going to consider an open ball around this root that is small enough that it doesn't contain any of the other roots of our polynomial. Then there exists an epsilon greater than 0 such that if the polynomial q, which is also of degree n, satisfies that the maximum difference between all the coefficients are less than this epsilon, then that ball around our root of p contains mu many roots of q, which is just counting for the multiplicities. So we're basically going to use this to compare the characteristic polynomials of J naught and J at our equilibrium. Okay, so we're going to prove that if DI is sufficiently close to D, then it's going to guarantee the local stability of the endemic equilibrium. So we're going to suppose that our system satisfies our assumptions and that the conditions in our previous lemma, this one, are met, along with B at 0 minus D at 0 is less than 0. Then there is going to exist a delta greater than 0 such that if D is less than DI is less than D plus delta, so basically if DI is only greater than D by a certain amount, then the trivial and endemic equilibria are going to be locally stable. And I'm going to run through a sketch of the proof. We're going to let lambda I be an eigenvalue of J naught with multiplicity mu I. Then we prove that J naught, all the eigenvalues of it have a negative real part. And because of that, we can find an open ball around this eigenvalue that basically stays in the left side of the complex plane where all the real parts are negative in it. So we kind of shrink this ball sufficiently small enough. And this ball also does not contain any other eigenvalues of J naught. Otherwise, it wouldn't satisfy the theorem. So we're going to let P of lambda and Q of lambda be the characteristic polynomials of J naught and J at our equilibrium respectively, or Jacobian at our equilibrium. So the roots of these polynomials are going to be the eigenvalues of J naught and J at our equilibrium respectively. Then through algebra, we are able to find m greater than 0, which is dependent on our parameters and such that all the coefficients of P of lambda minus Q of lambda are bounded by m times di minus d. Basically, this is directly the maximum between the difference of all the coefficients. So from the previous theorem, we know that there exists an epsilon. I'm doing epsilon sub I because it's dependent on this particular eigenvalue, where di minus d times m is less than this epsilon. And if you sort of do the math and rearrange it, you get di is less than d plus epsilon I over m. And we're going to repeat this with all of our eigenvalues of j naught and find the minimum of this epsilon. And that's going to be our delta. So if we finish the statement of our theorem, what we have is that if d is less than di is less than d plus delta, it implies that this ball around our eigenvalue of j naught contains mu I many roots of q of lambda. And so the idea is that around each of these balls of roots, or around each of these balls around the eigenvalues of j naught, we're going to be able to find the eigenvalues of j at our equilibrium, which demonstrates that the real part of all the equilibrium of j of xe are negative. Thus concluding our proof. Okay. We're going to arrive at some preliminaries which give a basic understanding of stochastic processes and stochastic differential equations, which are used in our model to sort of simulate randomness a bit. Because right now our models are completely deterministic, and if we run them, we get the same result each time. So a stochastic process is a set of random variables, x of t, where t is indexed from 0 to infinity. So it's like we're kind of going in a positive time scale. And x of t has a probability density function, p of xt associated with it. And we can get the probability that x is from a to b by integrating like we do with probability density functions normally. Now, some specific kinds of stochastic processes. A Markov process is a stochastic process that only depends on the current state of time and not on a previous state. And a Wiener process is a continuous Markov process where in a unit step of time, the change in the value of the process has a standard normal distribution. All right. So we're going to build up our SDE model. We're going to let E sub x be the unit vector in the x direction. So for example, E sub s is going to be 1, 0, 0. And the stochastic differential equation model corresponding to our deterministic model, basically we have a bunch of transitions of our value of x at a certain time. And that's going to be delta t is our jump in time. So x at our new time minus x at our previous time is going to be given by delta x t. And the probabilities of some given change of time, given the time that we were at, is in this table below. So each of these only depends at the previous time that we were at. We are assuming that delta t is sufficiently small enough such that all these probabilities are less than 1. And if you look at the compartmental diagram, each one of these sort of corresponds to us leaving one of our compartments and going to another compartment in our system. The stochastic differential equation model is given by this formula. If you kind of ignore this part right here, it already looks just like a differential equation model. It's just that this term sort of gives us this randomness. And that's what that dw of t means, because w of t is sort of representing the Wiener process, that kind of standard normal stochastic process. F is going to be the expected change in our x over time. And then h of t is given by v, and v is given by that expression, which that's kind of going to give us our sort of our term that has all the randomness in our system. If we notice, f is going to just be the f is just directly what we have in our system. So if you kind of ignore the h of t, this is just going to be solving this through Euler's method, basically. Or it's just going to be solving the deterministic differential equation. Kind of got ahead of myself because we talk about the Euler-Maruyama method next. We're going to let Tn be a set of equally spaced points in R with some step size h. And if we are given the Ito SDE of that form, then we're going to let X naught denote an approximation to X at time N. And then nu of N is going to be an observation of the standard normal distribution. Then the Euler-Maruyama method is going to approximate X at time T with this formula right here. So once again, if we sort of remove this last term, this is just the normal Euler's method, but all of our randomness sort of comes from this beta function right here from this expression, which is what is given by our H matrix down there. And that just kind of lists all the transitions that we have in this slide. Okay, so now I'm going to run these models. Now I'm going to show what we get whenever we run this through our stochastic and deterministic models. So we're first going to demonstrate an example that yields that commonly used equation for the Ali effect that I brought up earlier. We set B of n to be this linear equation, and then C of n to be this quadratic equation where they have these specific coefficients, where K1 is less than K2, and it does yield this once again. Now, if we let DI be equal to D, then this is directly the Ali effect model that we looked at earlier. But whenever we have a greater rate of infection, basically what that has on the system is that it lowers the equilibrium points by a bit. So in this next slide, we have solutions for our initial conditions are going to be 30 susceptible individuals, 20 infected individuals, and then 0 removed. And we're going to end up getting that our population at equilibrium is going to be about 50. And here's what we get right here. I am doubling the beta value each time. And this gives us some interesting results. But I'm first going to talk about what's going on in this. On this left side, we have our ODE solutions. And they do look very straight right now, but that's because we're just on a very long time span. There's actually a lot of interesting stuff going on at that very beginning point where individuals are getting infected and getting removed. Then we have the mean of the stochastic differential equation solutions. I ran each of these 1,000 times, and that just takes the average of each one, and it gives us a certain pathway based on that. And then for here, we basically take all of the endings of our stochastic model, and then we can make a distribution from it. And what we notice here is that as we increase beta, we eventually get that our population size is actually, I believe it is actually overall decreasing as we increase our beta. So in our very top example, it's going to be near 50, but it's going to start decreasing further and further until to the point where beta is so high that the amount of infected individuals are going to start causing the population to collapse because the death rate is so high. And something interesting is that, so I didn't actually list the end distribution of I over here because I basically collapses guaranteed in the stochastic models due to how high our death rate is. And what we see is kind of interesting is that it's endemic in the ODE solutions, but the infected individuals keep collapsing for all of the SDE solutions. And that actually causes the population collapse whenever our beta value is high enough here to actually not happen at all because the infected individuals just die out quick enough that they're not able to infect enough of the susceptible. Now we're going to go over another example. This will be an example where we have a linear crowding death rate. We're going to say that the death rate per capita is modeled by a linear function, which will be C of n is equal to C naught times n, where C naught is a crowding rate of death. And then we can obtain an equation that exhibits our stable states by setting B to be equal to that right there. And so in our next slide, we're going to have solutions with initial conditions. 40 susceptible individuals, 5 infected, and 0 removed. And we're going to end up getting an equilibrium of about 70. And so we're going to talk about what we get here. Once again, we are increasing our beta value. We see that the infected individuals die out to 0 very early in this. And I actually checked the number. That does indeed correspond to, we have an R naught less than 1 in this case. But whenever we increase beta up to this point, it increases our R naught to where it's greater than 1, which indeed results in us having an endemic infection. Same thing for our last case. And our stochastic model is acting a bit differently. It is endemic, or it is not endemic for this first beta value. And it's still not endemic, even though the deterministic one is here. But finally, we increase it far enough and it finally becomes endemic. And we can kind of see it in our distribution that we don't see really I at all because it just stays at where it's uniform at 1, but then it starts going out here. We have some values of I there saying that at the end of our simulations, there's so many individuals infected with kind of a mean of around 25 of those.
In that middle bottom box.
Yeah.
Are things supposed to be there?
Actually, that might possibly be the case. Yeah. I ran it for as long as I ran all the other models, but it could be very well the case that as we move on, the stochastic model starts to go towards 0 for the infected individuals. And that would change the end distribution as well.
You need the zero. It would mean that we would be reaching the disease-free equilibrium again if it goes towards 0. But that would just be in the stochastic place. Kind of the point of the differences here is that there's some differences between the stochastic model and the deterministic model. We haven't worked out what causes those differences, but it's just something that we see in our system. Now I'm going to go over one last one. In this one, we're going to say that our per capita death rate is not dependent on the population density, which means we set C of n to be 0. And then if we set B of n to be this very particular equation, we're going to end up getting our alternative stable states. So we have a solution with initial conditions, 50 susceptible individuals, 5 infected and 0 removed. And we actually end up getting quite different results for the total population at our equilibrium. We have, because this time I'm varying the death rate of the infected individuals. We have that the population at equilibrium for this is going to be around 50. For the next one, it's going to be around 33. And this is our collapse state again, so it's going to be at 0. So something else to notice at this system is it has a quite large basic reproduction number. I think when I calculated it, it was about 50. And because of that, there is consistently significantly more infected individuals than susceptible ones. And I believe the rate of reproduction to this is also pretty high. So they just keep getting replaced and replaced as we, as the simulation moves further. Right. And another thing of interest is that the stochastic model collapses before the deterministic one does as well. And then finally, they all just collapse at the end whenever DI gets to be great enough. All right. So just a recap of what we looked at, the implementation of alternative stable states in the SIR model so far had immutable demographic curves, but our new model allows them to fit qualitative or quantitative data. We have demonstrated the conditions that prove some nice properties, such as existence and uniqueness of solutions, the stability of our equilibrium points. And we showed some simulations, both deterministic and stochastic, that show our model in action. And that is the presentation. Are there questions? This would be in the stability, you would analyze for asymptotics. I'm wondering if that there's stable but not asymptotic, but repeat the cycle.
Oh, actually,
That would be pure complex eigenvalue.
yeah, actually, I was able to, in my thesis, I actually do showcase where that does happen. Yeah, we end up having, it's still stable in the end, but it just oscillates until we get to that. Yeah. Although, I don't know the conditions that lead to that.
One thing that's confusing to me is, so this E of n minus T of n being less than 0. So my understanding that's E of n is the birth rate as a function of population, and D of n is the death rate. So if B of n is less than D of n, around one stable, how can it stay there?
It's, I think I might have misspoke because, hold on, I will back up to it. It's, the condition we're looking for is B prime of n minus C prime of n. So like that B prime of n minus that D prime of n, because that's what that is equivalent to.
So that B of 0 minus D of 0 is negative, D of n minus D of n is negative.
For the existence.
Yeah,
So it's just B of 0 minus D of 0. It's not B of n minus D of n at all.
oh, I see it, yeah.
It was before that D of it was another condition, sum of D of n minus. Now, I would about.
In your assumption. In your assumption.
Judging by the proof, okay. You said it was in my assumptions?
I think it's needed for something to be well defined.
Yeah. Although now that I'm looking at it, I think I might need to check that again because that may very well be a typo just because it seems like this eigenvalue is corresponding to this eigenvalue and I just didn't catch it. It seems more likely to be the prime because like I said, if it is negative at 0, then that means it should be total population. All right. I'll have to take a look at that and fix it before I do my final.
That's just fine, it is fine, but that's B prime n minus D prime n. The derivative is prime part is gone. It is the B of B 0 minus B 3 still B prime D.
Oh, so it is still that? Okay, all right.
It is
Cool.
B prime 0 also.
Yeah.
Fine, yeah. Like n equal to 0.
Yeah.
Product will be. So, yeah, it's only at 0. There is
Yeah.
a need.
It's not for general n. So
Just let's see.
Okay.
It's the derivative equal 0, but that happens needed.
I was semi-confident on that part, just because I always knew that it looked weird compared to our other conditions in the hypothesis. Yes,
Did I hear right that you're not? Right now, you don't have an explanation why the results in the stochastic case are so different from the basic condition?
we don't have a very specific one, but just like judging by the fact that we're like talking about stable equilibrium and we're like starting at certain points, like my idea is that like due to the stochasticity, it's either going to like get into, we kind of have like basins of attraction around our different stable states. And my idea is that due to stochasticity, there's some chance that it's going to jump into this other basin, and then there's a higher chance from there that it will go to this other stable state, as opposed to this other one. But other than that, we did not do much analysis on the stochastic case.
Say then this randomness that you introduced there, do you think it's a contribution of that randomness is able to provide the results?
Possibly. Although I know that we constructed our stochastic differential equation model in a very specific way to reflect our deterministic model. So overall, I would have to do more looking at stochastic differential equations and see if there is some kind of known way to like taper whenever our system has too much variety.
I did.
Euler-Maruyama method? Yeah. Sorry, can you speak up? How to find it? I actually didn't really know how to find it in particular. I was just told that this was how I translated to that equivalent system of stochastic differential equations. I would have had an answer for you, but I would have to look more in depth about it. Oh. Oh yeah, this could be used for any system right here. Yeah, yep. That's just the Ito stochastic.
Question.
Yeah.
Sorry, but so where are you considering taking the research now?
Well, I actually wrote a bit like at the end of my thesis about where the research could be taken. Part of it could be like trying to figure out these different conditions as to what's causing the stochastic model to act so differently from the deterministic one. And further research could also be, all we were able to demonstrate with the endemic case was that there is a region of DI greater than D that causes our endemic equilibrium to be stable. There might be a way to get a better condition directly for DI that will demonstrate the stability.
Okay.
Main ones I have in mind.
Are there more questions? I think if there aren't more questions right now, let's thank Hunter.
Thank you all for doing that.
Oh, yeah, I see where this 100, it was just T(n) minus T(n) is less than 0 for all n greater than some constant. Up there, yeah.
Oh, we're talking about the existence and uniqueness.
Yeah, yeah.
Okay. Yeah.
You get the depth pressure is high, becomes too high with high population. That's what I think.
That dominates the.
Yes, I will tell you
Whereas is you can't.
kind of a bit of advice for future presentations. That I can follow things a lot better if there's more pictures.
More pictures.
And I
Yeah.
know I'm not alone. So,
My
but
grad
especially with this
yeah.
one, because you have a lot of parameters going around, and I have trouble remembering which is
Yeah.
which. So
If-
it was just a comment that
I don't
you're
know
not
if,
unusual in that respect.
yeah.
but-
And I don't know if you saw it last year, but I presented this at the graduate research conference. That one had a lot more pictures in it. So
Yeah,
I could send you that presentation.
No, it's okay. It was just a suggestion for future style.
Oh, yeah.
That,
Yep.
that you can communicate better to, especially to those of us who are not experts at modeling or kind of a experienced amateur. It's something.
Yeah.
But it's, well, I guess it's partly a matter of style that I prefer myself to spend, to make a special effort to emphasize pictures and qualitative explanations. And not to get too hung up in calculation because nobody can follow those. Or at least so it's just a word of advice.
Yep.
By somebody whose judgment you should not trust on the subject.
Yeah. I do appreciate it. Thank you.
But simulation is not. But, now.
Oh, I'm gonna stop the recording real quick.
This committee may have few questions to ask, so you guys can. Okay, ask you questions.
If the committee want refreshments this day,
I have no desire for.
I have one either. So,
So you can. Bring them out in the hall. Talk out in the hall.
yeah.